Oh, hold on. I think it picked it up. I think it is working. All right, Grant, I think you can hear me. All right, don't know what it did. Unplugged it and plugged it back in, and it seems to work now. All right, so those of you listening on YouTube, we've got variance and standard deviation, just var and SD, and I was talking about rounding. So the rounding, I mentioned variance is 1.37, standard deviation is 1.17, and I mentioned, why do we need to do that? It's rounding. We'll give some rounding rules, but in general, your means always go to one more digit than what we measured, and then the standard deviation, the measures of dispersion, go to one more beyond that. All right, so that's our variance and standard deviation. What about the range in IQR? Well, again, I just called it PRAC 2, and then I can just do range of PRAC 2 and IQR, PRAC 2, run it, and that's what I get. So just again, repeat the range. You can put the minimum and maximum, that'll work. Or you can do the difference between the range, the difference between the value. So that is 9, so range of 9. And then for IQR, you can just report what R gives. So IQR. Questions? Pretty easy to do it in R. All right, let's get to the frequency tables. All right, so frequency tables are going to be a little bit different. All right, I am going to show you how to do frequency tables by hand because it's important that you know. Why? You never know when you're going to work with frequency tables. All right, so I showed you how to do the mean, and that's kind of how we set it up, where we have the sum of our frequencies times our values, and then divided by the sum of the frequencies. That was our weights and the x values. All right, so we multiply the weight by our x. We do that for every row, then we added it up, and then we divided it by the sum of that weight to come. That gives us the average. We can do something very similar for our frequency tables. All right, so the frequency tables, the variances, the actual equation of our variances are listed here. So let me go ahead and move this slightly. All right, so our variances were the sum of our squares, so the sum of squares up at the top divided by our sample size minus 1. All right, when we have weighting, you have to remember that each of our x's had a different weight. And for our frequency table, each of our x's had however many times in there. Well, we have to go through and for each of those x's subtract the mean and then square it. Well, fortunately, since we have, let's say, 18 ones in that data set, we only have to do this part once, and then we multiply it by 18. So we multiply it by the sum of by our weight, all right, in order to get that value, and then all we have to do is add up that entire column. The other way to do it, so if we took this x minus x bar squared, we can expand that out using, the FOIL method, and then we would get something like this. And what you see is that sum of the fx squared is only on one side, because on the right-hand side, that minus n x bar squared part doesn't change. All right, so that minus n x bar squared, it's just a fixed number. All right, so what we're going to do is I'm going to show you how we can do this with a frequency table. So here's our frequency table. Move this over here now. All right, so this is our frequency table. What I'm going to show you, we're going to step through and calculate the mean, all right, first, and then I'm going to show you how I calculate the variance and then the standard deviation. So the standard deviation is simply the square root of our variance. All right, and I'm going to use all of the equations that we've learned. Can we do the median? Can we do the mode? Yeah, so the mode's pretty easy. We just look at whichever one is most common. So here's our mode, right? That's our mode, that's most common. If we wanted the median, we actually have to figure out how many points are here and then find the 50 percentage point. So it's a little bit more hands-on to do the median, and same thing to do the interquartile range. We can do it, it's just a little bit more hands-on. We're not going to worry about doing those for the frequency table. We're only going to show the means and then variance and standard deviation. All right, so let me get this opened up. Go back here. And I am going to open this up. And for that, if you get motion sickness, close your eyes. All right, we are centered. It's Catherine. Please stand up over at the board. Take that eraser, move to the left. This way, this way, this way. Keep going, keep going, keep going, keep going, keep going. Keep going. Keep going. Yeah, right there, right there, right there. Okay, so that's all at the end, and that must mean I must have most of the board. Cool, awesome. Thank you. All right, so we are going to start with the frequency table. We use mode across the board. We've got X, and we have our frequencies. And just remember, we have all of these X values. These are the values that appear in our graph. All right, so example could be, how many families have 0 kids, 1 kid, 2 kids, 3 kids, and so forth. And then frequencies represents the number of families with that number of kids. Or if we were out doing dispersion or spatial distribution of, let's say, plants of some sort, we're dropping a grid and we're counting how many of those plants are in that grid to get a measure, to get a frequency table like this. So we have 24 grids that didn't have any plants that we were interested in. We have 56 grids that only had 1. So some of you had this in college class. Remember that, Cody? Remember that, Nate? That raggedy flag? Some of you are going to be doing that this year. So how do we calculate our averages and standard deviation, variance? All right, well, we have our X and we have our F. So first up is to do that F times X value. All right, so we just multiply across our rows to get our values. 6, 1, 2, 72. Is that right? 15. All right, so then we have the sum of our Fx values. Right, so I can add up that column to get the sum of all of our x's. And I can create. All right, the sum of the f's represents our sample size. So I don't know what this is, but I bet it's going to be something even number, something that easily divides. 5. Yep, 200. Myself. Right, so sample size 200. So what we can do then is our average. This is 383 divided by 200. 383 divided by 200. 1.915. So 1. So that's our average. So what this is saying is that the average number of kids that each family has is 1.9. Now, we know we can't have 0.9 kids, but that's the number. That's the numeric average. And just like plants, we expect to see 1.91 planks in our grid, but we can't have that whole number, so we can't have those fractions. Right? But we need this in order to calculate our variance. Right? So there's going to be two different ways based on the equation. We have our variance. One type is the sum of our deviates over our sample size minus 1. All right, so that's our standard deviation, stable standard deviation. When we convert it to a frequency table, we're going to use our frequencies. All right, so the sum of the frequencies times our deviant squares over sum of the frequency minus 1. All right, so what we would have to do, we have our averages, and then what we would do is go and calculate this x minus x bar and then square. So x minus x bar, and then x minus x bar squared. All right, so two different columns to do it this long. Well, what's our x? This is our x. So we do 0 minus our average, we get minus 1.915, and then 1 minus that, so we have 0.915. And then we have 2 minus 1.95, 0.085, and then it's 1.085, 2.085. There's a pattern here. We just took each of our x's and subtracted the b. Right? So that is our deviate. But that's a deviate for only one data point each. All right? We have 24 of these zeros. We've got 24 of these deviates actually in our data set. We have 56 of these deviates in this data set. So, all right, but we still need to square it before we multiply. So I'm going to take this number, this 1.915, and I'm going to square it. Make it 3.667. All right, and then I'm going to take this next one, 0.915 and square. Increase. 0.085 and square. And 1.05. Things to know. Our average lies right about there. That's where our average lies. All right. And you can see is as our numbers are close to that average, our square deviant is really small. It's going to be close to 0. As we move away from the average, our square deviant increases. Okay? It increases in size until we get pretty large, and then it has a lot of effect on our variance. All right, so now we have our square deviants. We now have to account for the frequencies. So now what we would do is frequency times square deviant. All right, so I'm going to take each of those and multiply it by our F column. 88.008. 46. they were larger, right? But we had fewer of them. So even an individual point carries pretty big effect on that square deviant term, but we have fewer of them. That means they contribute less to the overall variance. You can see it's only 33, but we have 78 here, 40 here, 46 there, all around our peak. That's how it should be, because that's where the bulk of our data fall. So now what we do is sum up that column, and this represents the sum of our f times the x minus x bar squared term. We add that up. This is the sum of our squares. 88.8 plus 46.872 plus 441 plus 40.08 plus 78.246 plus 28.551 plus 33.374 equals 561.264. All right, that is our sum of squares. That is how much variation we have around that mean right now. As we add samples, this number will continue to increase in size. We're not done yet, because what our variance is the average of our square deviance. That's what a variance is. So what we're going to have to do now is to finish this out. We have 561.264, and we're going to divide it now by the sum of our frequencies, which is 200 minus 1. So 561 divided by 199, I get 2.82. As my variance. All right, standard deviation, simply the square root of that number. It's already in my calculator, just get it square root. And it's 7. That's right. That's it, square. 1.68. That's 1.68. All right. So I just did everything like we would have normally done it if we calculated it by hand. Right? It gets to the same point. The sum of squares. We had to get that, and then we divide it by our sample size minus 1. Now that's the long way. I think the easier way is to do this other shortcut, which is the sum of our x squares minus n x bar squared over n minus 1. And that gets converted as well to frequency tables fairly easily. So what we can do is just take each of our x's and square it first. Much easier. So 0, 1, 4, 9, 16, 25, and 36. All right, that's our x squares. Each of our x's. That's what we would do. But we have 24 zeros. We have 56 ones and 63 twos. So now what we have to do is take our frequency times our x squared values. Now you pull up your calculator. 63 times 4. 306. 16 times 18. 288. 25 times 3 is 75. 36 times 2 is 72. All right, so we have that. Now what we can do is sum that column up. All right, and we will get a number that is a little bit larger than that. 1040. 1040. We also need our n times x bar squared. So our n is 200. 200 times our average. We're going to square that. Did I add those up correctly? Did I add these up correctly? Should be what? 315? Cool. I say something's not right here. 315? 497. All right, so that's that 315, 497. So that changes that. It's the same answers. So we got this, and we'll go finish out these. So now what we need to do is finish this part. All right, so on the board we had sum of our x's, sum of the frequency x squared minus the nx bar squares over our sum of the frequency minus 1. Well, we have 1, that's 1049. We're going to subtract out 733 and 445. So 733 and 445. And then we're going to divide it by 199. So I got 315, 5 by 5. Slightly different than this. All right. Divide that by 199. 1.586. If I do this other one, 315.497 divided by 199, I get 1.585. And then square roots. So the difference was rounded. All right? Difference was rounded. Here, I had the average, I didn't round here, I rounded at this point. All right? And then this rounding carried over to where I multiplied it by the frequency, which then carried over to the sum of that column, which then carried over to our division in that variance step. Doing it this other way, which I consider this part much easier way and less prone to error, less prone to error method. We do the x squareds. I do the frequencies. I don't have to round, right? I don't have to round until I get down here, and even there, I don't necessarily have to round because I have my sum. I can type in that number, 1049, and then I can do minus 200 times our average squared and hit equals. Leave everything unrounded in the calculator and then hit divide by 199, and I can get the variance. Standard deviation, simply the square root of those values. So just the square root of 1.55 is 1.26. That's going to be basically the same. Square root of 1.56. That's it. It's actually not. We've done it before. Right? I've done it. If you've had the ecology class, we do it in the ecology class. Right? And the way that I've moved towards is this. This is how I've kind of switched it. So sorry, you guys probably had to do it this way. Right? We move it to do the x squares, do the fx squares value. Makes it a whole lot easier. Now, how do we do this in R? We have a frequency. How did we do the means when we have a frequency table? What's that? We did 2 vectors and then what? What were the 2 vectors? We have x and f, and then what do we do? Do what? Did we use another function? The what? The rect function, the b function, to make a single vector. So then our vector has 24 zeros, 56 ones, 63 twos, 34 threes, 18 fours, 3 fives, and 2 sixes. We have a vector of length 200, all right? And then we calculate the mean. We can do the same thing with it for the variance. We already have our vector that we use to calculate the mean. All we have to do is issue the bar or estimate to get our variance and our standard deviations. All right. So go ahead, get this data table back into R, data frequency table, convert it to the vectors, get it into R, and then we will check our functions. Works. Data table for those of you at home. Get it? Did it agree with what we calculated? Maybe slightly different?
Yeah.
So, did you get it? Hopefully. Alright, so here's mine. Alright, so first in order to work with the frequency tables, hold on, move this off to the side. Go. Alright, so in order to work with the frequency tables, we have to first convert our table into a vector. And we do so using the rep function. Alright, so I did just what we did. I made my x val vector, so the x, I don't like using x, right, because I use it so much to represent like what we have to type into a function, so I'll use x val. Alright, and what I did was I created the object x val, and the numbers are 0 to 6, so I shortened it by doing 0, 6, and that gives me a vector from 0 to 6 in whole numbers, so 0, 1, 2, 3, 4, 5, 6. Something short, you'll see it, you'll see me use it occasionally. But for the frequency vector, I made the regular vector, so I used the combine function C, then I've got my numbers. Now, what you can do is do a repeat function for every single value, or I took a shortcut, and this is what I did. I actually explained it. So we're going to use the rep function on a vector where we give it a times vector. All right, so we have our x's. If you think of it like this, we've got 0, 1, 2, 3, 4, 5, and 6. And we have our frequency vectors, which is 24, 26, 63, 34, 18, 3, and 2. All right? So what I did was pass the entire vector to, you can think of it as like something like that. These are parentheses holding the entire vector together. Right? I passed it to the rep function. And when the functions work or receive a vector, and this applies to addition, this applies to multiplication, division, any other function that we pass it, what it'll do is apply the function row by row, and then keep stacking the output one on top of the other. So it goes the rep function this way first, so 0, 24 times. And then it goes 1, 26 times, and 2, 63 times, 3, 34 times, and so forth. And it goes row by row until it gets to the very end, and then it says, there's nothing more, I must be done. All right? So when I created this rep, it does the rep, and every time it just keeps adding on to the output until it reaches the end, the output's done, and then I save it as the dat vector. So here I called it dat. Again, I probably used dat a couple other times, and I did, but I have 170 values in there right now. So if I run this, you can see that dat goes 100. Did I miss numbers? 56. 56. 56. So we'll update that 56 times. All right, that's better. So 56 times. So that's better. 200. So I see that I got 1 to 200. All right. So I made my vector, and then we're just going to calculate everything using mean, var, SD. So we use the weighted.mean function. You could have used the weighted.mean function to do the mean, but you can't use it for variance or standard deviation. We have to create our vector. All right, we have to create our vector, and then once we created our vector, then we use the var and the SD function. Questions? What about everything else? We could do everything else. So longhand calculations. So we can get the squared deviance. All right, we know what our mean is, right? So what we can do is do our vector. So dat is our vector. All right, and I can do dat minus the mean of our dat. And again, it's using the same vector approach. We're working with vectors, and we're going to go row by row. So if I do mean minus, if I do my dat vector minus the mean of the dat, and I run it, look at what it gives me. It gives me all of the differences of the mean row by row. So I have 200 data points. This looks familiar, right? Minus 1.915. We calculated it in the frequency table. That's our x minus the average, right? The 0.085, that's in our frequency table, right? We've seen all of that, all right? But that's only part of it. That's our deviate, right? We need our squared deviate. So, I put this in parentheses, square it, and run it, and now you're going to see the squared values that we calculated. And again, we're going to get 200 values because when we work with the vectors, it goes row by row. But that's not everything, right? We want the sum of that. So there is a sum function. And now, when I run that, I get my sum of squares, which is what we calculated, 315.555. Comes out, better when we did the x squared and the fx squared, calculations because we didn't have to round it. So that's the sum of the squares. You looking for the caret? Did you find it? Yeah. 6. Yeah, number 6. All right. And then it's as simple as doing our division. So we know we had 200, right? Or we can do the length of our data. Oops. Let me get parentheses. All right, so that because it's the length of our data minus 1. And then we get our 1.585. So, things you can do it longhand, I say just do it. Use the var, use the SD functions, use what's built into R. I think we also asked to do like median and interquartile ranges, right? We have our vector, so right, just use the vector that we just created. So median of dat, that'll give us the median. The range will give us the range. IQR will give us the IQR. Right? All of those things. We already have the vector. All of these functions would take a numeric vector. Here it is. Here's our output. Could we use the summary function? Yeah, we can use the summary function for some of them. Right? It'll give the min and the max, which is our range. It'll give our first and our third quartiles, which, that's basically our interquartile range. It gives us the median, it gives us the mean, provided a lot of information. Pretty easy, not too bad. Not too bad. All right, any questions? All right. So, yep, we have this. Use the C, use the rep. All right, so what I think we're going to do is stop here. This is the coefficient of variation. We'll pick up on that. Actually, no, we'll finish this out. So coefficient of variation. Yeah, this is it. Sometimes we want to know which variables, which measurements are more variable. So is wing length or tarsus length more variable? And you'd be tempted to just compare the variance or compare the standard deviations. But that's really not the right way to do things. All right? So here's an example of why. All right, we're going to compare heights in this class. And we measure everyone's height, and let's say we measured it to inches. All right? Can we calculate a mean? Yeah, we can. Can we calculate a variance? Yeah, we can. All right? So now, once we do that, now what we need to do is get one more measurement. And let's take a single hair thickness. So hair varies in thickness, right? Everyone contributes one hair, we measure the thickness. Does that have a mean? Yeah, it does. Does it have a variance? Yeah, it does. Right? So if I ask you which one is more variable, what are you going to answer? Height or hair thickness? Why would you say height? Yeah, so it's easier to see the different sizes than the thickness of hair. And big reason why is their heights are larger. Right? Much bigger measurements. Yeah, the variance will be much bigger, but is it necessarily more variable? No, because what that type of question is asking is saying, we have our mean here, All right? We have our mean here at that x bar. What we want to know is our variable, are all of our measurements, did it look something like this, or does it look something like that? All right? And when we did hair versus height, we've got x bar up here, we've got x bar down here. You're looking something like this. You really can't compare the raw measures of variance or standard deviation because we're at a very different level, very different magnitude. So this is where our coefficient of variation comes into play. It's going to take our standard deviation and divide by the average. So what we've done then is our standard deviation is going to be some number with the units attached to it. Our average is going to be some number with the units attached to it. And then those units cross out. And that gives us one single value that is now comparable no matter what our measurement level is, what our magnitudes are, and so forth. All right? So the coefficient of variation is simply our standard deviation divided by our mean. We typically multiply it by 100% to get a percentage, all right? But we don't really have to, all right? We do typically report it, so I can look at the decimals and say, oh, it's 0.76. Yeah, I've got 76% variation around the mean. It's kind of what it's describing. Now, coefficient of variation is biased. It's below its actual true value. So they do have an unbiased estimator that is used that way, but we're not going to do that. We're not going to use it because what ends up happening is as our sample sizes get larger, our bias starts to become negligible. All right, so when do we use it? For comparison of variation between the groups. So when our means are different and also when we have different units of measure, we would report the CV. All right, so we have an example problem for CV, for coefficient of variation. We have DAT1 and DAT2. And that DAT1 and DAT2 were these data points, so these vectors. So we made them at the beginning of class, and the question is, which one is more variable? We already know the variance. Let's calculate the coefficient of variation to do this. Is there a coefficient of variation function in R? No, but you can do it by hand. All right, let's go ahead and do that. You guys get it? Hopefully. Yep. Okay, question on setting up frequency tables. Nope, you get the same answer, right? Yeah. Yep, no, that works. That's how I introduced it the first time, where we did rep of 0, comma, frequency, and then comma, rep of 1, and then a comma, rep of 2, and so forth. All right, so move this over here. Coefficient of variation. You know, we don't have a built-in function, so what you do is just you calculate it yourself. I've got standard deviation of dat1 divided by the mean of dat1. Each of these gives a single value, so we just write the function, and then I multiply it by 100, and I repeat it for dat2. So dat1 it didn't make. Oh, because I called mine prac1 and prac2. That's why. Let's fix those. Prac1. Yep, so if you called yours something differently, go ahead and correct it. Prac2. There it is. So you can see the smaller measure actually had more variability to it. 17% variation around the mean versus 15% variation around the mean of the larger values. It doesn't always work out like this. Sometimes the larger or the smaller numbers have less variability, but you know, we have to use the coefficient of variation anytime we ask that question, which is more variable. And you should remember that, because sometimes if we're doing morphometrics and someone wants to know, well, which trait, which characteristic is more variable, you may be tempted to do variances. But you have to remember, if we're at different sizes, if our means are different, especially if they're drastically different, your variances are going to be drastically different. So what you need to do is actually calculate these coefficient of variations and compare those to see which is more variable. All right? Questions? So I was just looking to see where this next homework assignment is, and it's not up on Blackboard, so I think I might have an R markdown for you. I'm going to go get that taken care of. But that is going to get posted. So just to kind of show you, this isn't quite it, but this is example practice, you know, exam 1 review. This is going to be optional that you can do like over the weekend in preparation for the exam. I do say do this stuff by hand in an R, but you know, we're really not going to be doing stuff by hand. It's all going to be in R, so you're going to have to feel comfortable, you know, getting these data, getting these vector into R in order for you to calculate these values. So mean, median range, interquartile range, variance, standard deviation, coefficient of variation, frequency tables, and then I have some data sets too that you can practice getting into R and checking some things out. All right. So the homework assignment's kind of like this, minus these bottom ones, where it has you just practicing calculating the descriptive statistics. All right, so we'll get that posted. I think those will probably be due on Friday. I would suggest try working on it a little bit earlier. So if you have questions, we can answer it on Wednesday. All right, questions? So I think our exam stops at this point. So we're going to stop at the end of descriptive statistics. And then exam 2 is basically probability. All right. So bring a calculator. All right. If you wanted to stay here and work, you can. If you want to take off, you can. Have a good one. Enjoy the 80-degree days that we're having.